Okay, thanks, Wenjie, for the introduction. My name is Yuandong. I'm a research scientist in Meta AI Fair. Today, I'm going to talk about some basics about reinforcement learning and its application to computer systems. Because this tutorial, this talk has only 30 minutes, so I basically try to compress everything into maybe 60 slides to make sure that people have an rough idea about what reinforcement is about, and some of the pretty famous applications that you can leverage reinforcement to solve these problems. So first of all, I want to cover what is reinforcement and what it matters. And the second and third, we're going to talk a little bit about the two different branches of reinforcement learning. That's called value-based approaches. This include Q-learning, AlphaZero, with a case study of AlphaTensor. And finally, we're going to talk about a policy-based approach. This includes the policy gradient, active critic, BPO, and also an application that try to leverage active critic to network planning problems, which is a system problem. So let's start with these slides. This is a kind of like a good slides that show reinforcement is useful for many kind of situations, especially in games, right? So we have seen a successful stories in different kind of games like Go, chess, shogi, and maybe Dota, StarCraft. So there's a big success there. And recently there's a resurgence of reinforcement learning being used in the ChatGPT and GPT-4 this chatbot. Right, so what they do is that you first train a supervised agent with lots of data using language models, and then you can basically train a reward model on this comparison data. And finally, you can basically tune the language model with reinforcement learning. So this basically shows that reinforcement will play a role in building the state-of-art chatbot, state-of-art this kind of QA systems. So today I'm going to talk. I'm not going to cover this part because it's kind of beyond the computer architecture and computer system domain. But we're going to talk a little bit about a modern system side, how can system people want to use it, reinforcement learning, and why system people want to care about that. Right. So here's two motivating examples. So people may already see there's AlphaTensor and also AlphaDev from DeepMind. What they do is they are trying to leverage reinforcement learning to find what is the most efficient matrix multiplication given two matrices of size n by n. And also recently there's AlphaDev that try to find what is the shortest assembly code so that you can sort three numbers or to five numbers, etc. Right. So they are both using the same kind of technique called AlphaZero, and I'm going to introduce later. So in the higher level, why system people care about IO? This is because in the system side, people usually think about a multiple access to be optimized. Right. So people talk about memory usage, latency, and efficiency, etc. There's a lot of access they want to optimize. And if you want to think about this as optimization problem in high-dimensional space, usually what people will do is that we start with some kind of initial solution, and then you try to find a way to improve that in a sequential manner. As long as the problem is modeled as a secure decision-making process, then you can use reinforcement learning to actually improve existing solutions and to find a better solution. That's how reinforcement is being used for system side. So in this tutorial, we're going to cover a bunch of possible optimization problems. Right, so this include combinatorial optimization. This include, for example, the network planning problem. I'm going to cover in a very short amount of time, and also we also want to cover compiler optimization by Christ. Right, so on the other hand, we can also use reinforcement learning to model multi-party optimization. So in this part, Wenjie and Mulong will cover how can we leverage IR to find the best attacker and also defenders in the cache timing attack problem, which is also a hard reinforcement hard system problems in computer system architecture domain. Okay, so now let's really come to this page that what is reinforcement? We'll talk about reinforcement for 5 minutes now, and people have no idea what is higher, right? So for reinforcement learning, I think here's one figure that try to show what it is, right? So we have an agent, okay, some agent here, and the agent will actually perceive the word, and the word perception is compressed into a state S, right? And then agent will see this state S, and it will take an action. The action will change the environment as well as change the agent's behavior in terms of state, and then at the same time, the agent will get a reward, right? So you basically do this in an iterative manner. Okay, so here's one example. So suppose you have a maze here, and you have a red dots, which is basically the location of the agent. And the state here is basically where is this agent? And action is that the agent is going to be moving left, right, top, and bottom. And next state will be like where will be the agent after that move. So in terms of mathematical language, if we put like a coordinates x and y into this two-dimensional maze, then we can basically use two numbers to represent the state of the agent. And also the action will become like a subtraction or addition of one of the numbers by one, right? So that's very clear. Oh, okay, cool, thanks. So if we do this iteratively, then what happens is that you're going to have a trajectory, right? The trajectory starts from S1 and you take an action A, it will give you state 2, and taking action 2, take you state 3. And at the same time, you also get reward. Okay, so what is the reward? Reward is basically to say like if you choose action A, what will be the return from this action, right? So for example, in this kind of particular scenario, suppose there's a goal state. And the goal state is basically the exit of the maze. And the goal of this agent is try to find a path all the way to the goal state. And then you can exit there, right? So then like if you are closer to the goal state, then you will get a high reward. And this will basically trigger the agent to move towards the destination, right? So the goal of reinforcement learning overall is to maximize the long-term reward by maximizing this like a capital R functions. And that long-term reward usually is a linear combination of all the short-term reward, one-step reward. And here the gamma is a discount factor. Basically means that you want to favor short-term reward, but you also want to consider long-term reward as well. But the long-term reward will be discounted using the discount factor gamma. That's how that's basically the goal of reinforcement. You basically want to find like what is the best strategy to move around in this world so that the long-term reward is maximized. Okay, so there's a few key quantities. There are a few key quantities in reinforcement learning. And so, for example, here you have 3 of them, right? So first of all, you have this policy, which is basically the probability of taking action A given state S. You can also have like Q function and a V function. That is basically like the reward starting from the state S and the basically expected reward out of it. And the difference between Q and V is that in Q function, you try to find what is the expected reward if you start from S and taking action A. But for V, basically that's the reward you can get if you start from the state S, but there's no like action condition in there. So for all these 3 properties, as long as you get one of them, it's sufficient to find optimal strategy. Right. So for example, if you manage to get like a pi, which is a policy, then just follow the policy. You just say, oh, given the current state, okay, I will check the policy book. Policy playbook say, okay, you take the action A. Okay, just take action A. It will give you the optimal strategy, right? Similarly, if you already have the Q function, then what happens is that given the current state, you go through all the A's, and then you basically get like a vector of the Q values and pick the best one. Then you basically also get the best policies, etc. So then like given these 2, then you actually have 2 different pattern methods, right? So if you optimize the policy, it will give you a policy-based approach. If you optimize the Q function, it will give you a value-based approach. That's basically the second part, right? So I'm going to cover a little bit about the value-based approach first, and then I will cover the policy-based approach. So first, let's cover the value-based approach. So for a value-based approach, we want to optimize Q. So how are we going to optimize Q? It's actually pretty simple, right? So consider that Q is actually a table which has like a lot of slots. So if you have a number, the number of states is like S and number of action is A, then the Q table will become S times A. So this kind of Q tables. And your goal is trying to just fill in these tables until your table is optimal, then you just follow optimal policy, right? So what do? Basically, very simple, right? So you get like few trajectories, and for each trajectory, you update these Q functions using this formula. Right? So if you update that for sufficient time, then the Q function will be proved to be converging to the optimum Q, then you are done. However, the world is not as nice as that, because in practice, Q function may have exponential number of entries. right? Because the state can be exponential, and A also may be a continuous value. So in that case, like people come with this deep Q learning idea, in which like we can replace the Q function as a table by a parametric function, which is represented by a neural network. So you have a neural network, the neural network will directly give you Q function given S and A. Or the neural network will give you the list of A given Q. Right? So these are all basically different approaches. You can parameterize Q functions. So once you have the parametric function, then what you do is that you can just secure this Q function every time. And this Q function is going to be generalizable to basically like a new state that you have never seen before. And this is actually the benefit of using the deep models. So, but if you directly optimize that function, it will lead to instability because you see like on both sides, they're going to have a Q, and this Q are parameterized by theta. It's going to be unstable if you train the models. So people basically think about like different hacks in order to make things work. One hack, it would be like you basically want to fix the Q function that is on the right. And then the Q function's parameter is also fixed, use the old fixed parameters. And then you use that to update the Q function on the left-hand side, right? So that's actually like the way you update that, but there's still issues. The issue is that after this update, it may change the Q theta function substantially. This will also lead to instability. So then what we do here is that we can actually make the target even smoother, which means that we don't need to want to update the Q function in one shot, but you want to update the Q function in a kind of gradually manner. So you still have the Q function in the right-hand side, but now you have a kind of like some kind of correction term. That correction term is called the temporal difference error, so TD error. So the correction term is basically the difference between the current Q function and the Q function that according to the future rewards. Right, so you basically do that and update, and then overall you will give like more smoother updates, and the algorithm can converge. So this is called the DQN algorithm that's being simply published in Nature in 2015. So here's like a one simple like a video showing like how people see this functioning, this algorithm functioning. You start from like a very simple games, and that game is basically like when people play with this game. Called breakout, right? So you basically move the paddle around and pick the ball, and so the ball bounces around to kick out all the bricks on the top. At the beginning, the agent is like doing like a very bad thing, so you miss the ball all the time. But over time, when you keep training the Q functions, then it will become like much better, right? So it will basically like try to basically pick all the balls that is bouncing around, and finally can clear up all the bricks on the top. Right? So that's how the thing works. Okay, so there are like multiple different like extensions that you can leverage for solving the Q learning problems. The first basically the first approach that people were thinking about, and it's very effective, is called multi-step Q learning. So instead of like going one step further and retrieve the future Q and use that future Q to update your current Q functions, you can basically go forward multiple steps. That's called n-step rollouts. Usually this will basically give you like more accurate estimation of the future values, right? So and this basically is like one of the standard approach people will use, right? And another like thing that people will come about is called replay buffer. So the trajectories here are basically all generated by the previous policies. Right, so usually the previous policies, you run them, and then you collect the trajectories into a replay buffer, and then you get the data from the replay buffer and basically like execute your learning algorithms. So that's basically the idea of replay buffer. And for the replay buffer, it's actually, you can see this as like a dynamic data set. Right, the data set has a lot of experience, and you take the data sets inside, and you're updating it at the same time you train these models. Right. But if you think this concept of replay buffer a little bit more, then you actually think you actually realize that this is actually very different from supervised learning. Right. So this actually gives you this difference between the two concepts in the reinforcement learning. One is called on-policy, and the other is called off-policy approaches. So for off-policy, it's very simple. It's kind of like supervised learning. You have a fixed data set, and you train your reinforcement agent on the fixed data set. Right, so the fixed data set can be collected by expert behaviors, or can be like coming from some like historical data. But on the reinforcement side, there's another kind of like branch of algorithms that are called on-policy. In that on-policy, usually the data sets are sampled by the current models. And the data will actually be updated again and again once the model get updated as well. So in reinforcement learning, a key difference here is that agent not only learns from data, but also choose which data to learn. This is actually very interesting. So this is kind of one example, right? So you start from like one state, and then you first collect a few data on like one branch of the space, and then you start to explore another branch of the space, and you collect more data, more data, more data. And then the data become larger and larger and cover larger space, and your policy become more stable. But there's also always a trade-off because the space is exponential. You cannot explore every possible state. So there need to be a trade-off. So one way to handle this trade-off is what is called Monte Carlo tree search. So in my tree search, what happens is that you try to update your Q values on the fly, depending on your exploration. And once you have new explorations, and that exploration will basically lead you to update your Q functions. And then you explore the space larger, and at the same time, your Q function becomes more accurate. Right? And the Monte Carlo tree search, in some sense, is optimal in terms that, I mean, in the long run, if you run like a sufficient number of trials, it will eventually cover the entire search space and give you optimal policies. So along that line, you actually see like a lot of applications. This includes DeepMind's AlphaZero series, and they are basically using this kind of loop in order to optimize and to find like what is the optimal policies, right? So this loop is actually quite simple. It's exactly like what I just said. You start from this Monte Carlo tree search, and then you collect lots of data. And then once you have lots of data, you update your current models using reinforcement learning, and then you use this updated model to generate more data. Right? So then you do this kind of iterative approach until you actually get good solutions. So that's and this work leads you to like a superhuman performance. Right? So we also follow the same kind of paradigms. This is one of our work in 2019. That we actually are able to create a very strong Go bot that can beat professional players in a single GPU. These professional players are all coming from like Korean Go associations, and basically no one can able to beat it in a finite amount of time. So recently, DeepMind also comes with this AlphaTensor approach. Basically, this one is also a kind of application of the AlphaZero kind of method, right? So the question of AlphaTensor is how to multiply two matrices of size n by n, but with a small number of multiplications. So it's we all know like a stress is a matrix multiplication. You can multiply two by two matrices with only 7 multiplications. But what happened with larger and larger and larger matrices? So in that case, like we actually can write down the AlphaTensor, write down the matrix multiplication formulation as this follow objective. Basically, mathematically, you can show that you want to this is equivalent to minimizing the rank of the third order tensor. And this third order tensor is written as the following kind of formula, right? And this Tian is a predefined tensor of size n squared by n squared by n squared that represents this multiplication structure of these two n by n tensors. And you want to find what is the best decomposition of this Tn so that the composition will have the fewest terms. This term is called the rank here, right? If you have fewer terms, this represents that you have fewer number of multiplications in the final algorithms. Right, so the goal is to search this U, V, and W so that this constraint is satisfied and the I is minimized. So what they do is very simple, right? So you basically treat this as a reinforcement problem, right? You start from the original state in which S0 equals to this Tn, this kind of tensors, and then every time you try to find an action, this action consists of U, V, and W, and then you basically subtract this term from this tensor, and you get S1. This is new state. And then you do this iteratively until hopefully at some point your ST becomes 0, which means that you actually arrive at the decomposition that has all the rank 1 terms. And your goal is to find like this ST goes to 0 as soon as possible. Right? So that's basically like the correspond to the lower rank solutions. They basically like use this AlphaZero kind of approach in order to solve these problems, and they actually find new matrix multiplication schemes so that the number of multiplications is smaller than the best known rank. Right, so that's actually pretty impressive. With this kind of combinatorial optimization problem can actually be solved in this manner. Okay, so yeah. The dimension of S here is so is equal to dimension of Tian, right? And Tian is a third order tensor. So okay, if you come back here, so if you have n squared by n squared, n squared, right? So for n is equal to 2, then it becomes 4 times 4 times 4. This is 64 dimensional.
So it's dimension 64.
Yes. But it may have lots of, there's a combinatorial structures there, right? So it's basically exponential. Okay, so I will quickly also cover the second part. Sorry, I need to, because it's a tutorial, so I don't want to cover like too deep, but we want to cover like many different directions, and so that people have an overall picture about what reinforcement is doing. So we also can do policy-based approaches, right? So as I just said, as long as you optimize, you get like a one kind of key quantity solved, then the problem is solved, right? So the policy-based approach is basically trying to focus on policies. You want to basically learn a policy directly in order to maximize your overall rewards. Right? If you write down the objective function j theta here, the objective function j theta actually consists of these policy functions directly, right? So you basically get trajectories from the policy functions, and then you can basically like find cumulative rewards along the trajectory, and you want to maximize that objectives. So after some mathematical manipulation, you actually can come up with this gradient of this objective functions. And the gradient here is in terms of still an expectation, but it's kind of like a summation of this scoring function and the reward. Right. So the good thing about writing this as expectation is that you can instead compute this entire expectation. You can basically do a sampling approach, right? You can sample any kind of trajectories with these policies, and then you basically like approximate the gradient with respect to the trajectories, right? So then you have approximate gradient, and you can use the approximate gradient to update your thetas, etc. And here, the reward here can take different forms. It can be just like as simple as just the reward by definition. So that's basic definition. That's the reward function you can get. But it can also be basically like a combination of the n-step rewards and the final v functions that is being estimated. We estimate the future rewards and put them together. It can also be maybe like just a q function that is being estimated at some point. Right? It can take different forms. But the issue with policy gradient is that if data are on policy, then it's learned quite fast. But if data is not on policy, then there's some issues. Right? So you really need to have data to actually drive these entire algorithms. Right? So if there's this basically means that if for every data point have been used, and the data points once it being used to update the objective function, you have to throw this away. Right, so because the data is no longer on policy and the policy has been updated, so you cannot just use that on policy data to update your algorithm again. That's actually bad. Right, so this is actually a lot of waste in terms of the computational time. So then people come with these kind of off policy corrections. So how we do these off policy corrections is that we actually add a term in the gradient. Right, so in the policy gradient approach, we have these clean forms. But when the data come actually not from the policy itself, but come from some behavior policies, beta, which is not necessarily the same as the current policy, you actually add the additional term roof t, so that the final estimation of the gradient is still unbiased. Right? So here, this roof t is an important sampling factor. That is the ratio between the policy that's being currently used and the behavior policies. So basically the ratio of the two, right? So obviously if pi equals to beta, then this root t will be 1, and it will come back to the original policy gradient updates. But then there's a problem. The problem is that the root t can go to infinity, right? So if you actually hit action that you have never experienced in your behavior policy, right? But you actually experience like one in a lifetime, then this root t will basically blow up. So in practice, what people do is that there will be a cap for the root t, so that the problem, the estimation is not unbiased, is not unbounded. So and then the algorithm can be pretty stable. So based on the policy update, policy gradient update, so we can also improve on top of that. So that's basically the algorithm. Usually people call this actor critic. So what they do here is that instead of using the Q function as the reward in the policy gradient, we can use the advantage function. The advantage function is trying to basically find the relative advantage of an action relative to other actions, right? So here is a very simple illustration. You start from state S, you can roll out like a multiple different trajectories, and some of them will basically give you, for example, higher than average return. Some of them give you lower than average return. Right, so the advantage will be like basically the advantage of one action compared to other actions. Right? So that's basically the definition of advantage functions. You use that, and once you use that advantage functions, and also you use the functions to compute advantage functions, then in your algorithm you have to estimate both the policy, which is pi, and the value functions, which is q or v. Right. So then this algorithm actually become called actor and critic, in which like you are optimizing both the actor and also the critic at the same time, maybe with different parameters. That's the definition of the critic algorithms. And one of the famous actor critic algorithm is called proximal policy optimization, abbreviated as a PPO. So these algorithms, what you do is actually exactly the same as I just said. So you have the advantage functions, and you also want to clip this rule, which is the importance factor, so that the rule is not going to be too far from one, right? So, and that algorithm is called PPO. It's actually being widely used in many different scenarios, and including the OpenAI 5 for Dota 2. There's a bot that can beat like professional Dota players. And we also see PPO being used in like IHF in many different scenarios. So this is actually one of the very widely being used algorithms in practice in the reinforcement literature. Okay, finally, we have like maybe a few minutes left. I'm going to talk a little bit about the application of using reinforcement learning for network planning problems. So this is a paper that we have published in ASCA 2021. So in that problem, we are dealing with a very concrete like a system problems. Is that you have like a network that has n different nodes, and these networks will have interconnect capabilities, right? So for node A and node B, there's a connection, and the connection can be a fiber, it can be a cable, it can be whatever. And you basically want to borrow these different capacities to basically meet the needs of the network like data flows. But at the same time, you don't want to use too much money, right? So there's a minimization of the cost. So the entire optimization problem can be written down as the interlinear programming, right? So in that case, like there will be an operator function, and you want to minimize some cost, overall cost for basically like borrowing different fibers at different sites. But there is a constraint, right? So the network flow need to be conserved, and there's a link capacities, and there's a lot of other capacities constraints, and also you don't want to like change your current topology for too much. Right, so basically, there's a lot of constraints. But if you want to solve this problem from scratch, I mean, there's a lot of solvers, like IRP solvers, but it's very tricky to use it because the problem itself can be huge, right? So it may take days or weeks in order to solve this problem, but from scratch. So in order to do that, usually people will design their own heuristics to trade optimality for tractability, right? So you want to find, maybe we can solve a small problem first, and then combine all the solutions together, right? That's one possibility. Then this will be one solutions, but we want to find like many better solutions, right? So then the key problem here is it's hard to find feasible solutions for this IRP problems, right? So how to do that? We basically train a reinforcement agent to actually like solve these problems. So you start from this problem description, which is a network, and also all the capacities at different edges. You basically train an reinforcement agent to propose an initial solution. And then we basically feed this initial solution into the IRP solver. And then IRP solver will give you the final solution much, much faster. And also at the same time with high quality. That's basically how it works. So basically it's a two-stage approach, right? For stage one, what do we do is that we start from the topology. The topology is being given. It's basically the problem specification. At the beginning, there's no capacity. at every edges of the topology. And every time the reinforcement agent will find a way to add some capacity at some edges, right? And then it will keep adding the capacity until at one point, problem, the solution becomes feasible. So that's basically the entire trajectories. Right. So and the reason why we think this is more reasonable than like just solve the entire problem in one sketch is that it's much easier to check the feasibility of problems than to find the optimal solution of the problem in one shot. Because the feasibility check, it can be done and it can be accelerated in like a lot of with the different like aspects. Right. So for example, what you can do is that you can basically shrink the graph by source aggregation and basically by merging different nodes. And then we check if the aggregated problem is not feasible, then okay, the original problem cannot be feasible, can get rid of that. Right. So there's a lot of shortcuts you can use to do feasibility check. So you basically leverage like a reinforcement to learn what is the best policy to add different capacity at different edges so that the problem becomes feasible as soon as possible. Right. So once it's done, then we can actually go to the next trajectories and keep running. So and the reinforcement architecture, yeah, sorry.
Basically, you said LFP is kind of essentially brute force data scientist, and then what you're showing here on this slide is compared to IRP?
No, I think for IRP, because it's a very general solver, right? So it may not leverage the problem-specific structures, right? So for this one, because you already know the topology, right? So in the reinforcement, trying to leverage the structure of the problem to find the best policies. Yeah.
So what's the math that's involved in this kind of approach? What are the key mathematical operators here instead of ILP that you use for this approach?
I think that okay, so I'm not sure if I understand the question. So here we are basically find the optimal policy so that you can, intuitively increase the capacity at every edges, and the capacity being added may have maybe a function of the actual network structures, right? So human may have their own perception. If you say, okay, here's the bottleneck. Yeah, then it seems like there's a bottleneck, then we need to add more capacity in this bottleneck to solve the problem. Okay, so for this one, it's actually as easy as like you just like find like what is the solutions there, right? So you basically find like it's basically this one, right? So you basically check like whether this topology is feasible. If it's feasible, then like yes, and you basically the problem is solved, and you basically go to the second stage. If it's not feasible, then you go through the reinforcement agent and you pick like the capacity there. Yeah, that makes sense. Okay, so in terms of the reinforcement architectures, it's very simple. You basically like put all the features and topologies into a graph neural network. And then you learn a graphic embedding, and that embedding will be used to predict the actions as well as the rewards, as well as the critic. So that's the actor and critic network. And the actor will basically pick which like edges to add capacity, and the critic will tell you whether it's promising to going through that line. Right. So you basically learn actor critic agent to find the way to add your capacity over time. So and the stage 2 is very simple, right? So once you have reinforcement solutions, what you do is like you can basically add the solution back to the IRP solver, and then you only allow IRP solver to search in the local vicinity of the reinforcement solutions. And this will actually make things much easier because you already have a feasible solution as a reinforcement solution, and IRP will be able to leverage that in order to find better solutions, because this reinforcement solution gives you a lower bound about how things can be. So it's much easier for the IRP solver to solve the problem. And finally, we actually find that our approach are able to give you a solution that is better than the heuristics, and in terms of like a lower cost, at the same time can deal with like a larger non-network topology. So here A, B, C, D, E are 5 different topologies, and E is the largest. And you will see that if you just solve IRP solutions from scratch, and for the last 3, it's basically like for the last 4, it basically gives you like infeasible solutions yeah, given like a short amount of time. But we are able to find good solutions, and at the same time, it's quite fast for larger networks. And the code is already online. If people are interested, you can take a look. Okay, so this concludes my tutorials. So let me know if there's any more questions. Yep.